So, population of deer herd goes from 8 to 26 between 2017 and 2020. 26 to what? Between 2020 and 2023? Triples plus a little bit. So if we triple this plus a little bit, tripling time, again, being the same, just like doubling time is, you can easily prove that, the same way you prove doubling time is constant, which we did. You find that it's got a little more than triple. If it tripled, it'd be 78. Little refined estimate gives us 84. Ratio approach, if we got 26/8 of what we had in 2016 after 3 years, then we should have 26/8 of that after another 3 years. Comes out a little over 84. 84 and a half if I did it right. Okay, now let's do the more rigorous thing. Although this is plenty rigorous, it's not going to help us much with 2025 because that's a 2-year time period. Now you might guess, well, if it triples in 3 years, it's going to double in 2 years. That's not exactly right, but it's not going to be that far off. So you can make a ballpark estimate that maybe it'll be up to about 170, 165 to 170. Let's do this more rigorously by doing this. Here's a graph for population versus time, and let's call the graph, this is population, and this is time since 2017. Okay, in 2017 the population was 8. So we're going to put, now we've got to get some pretty big numbers here. So I'm going to put 8 here. Okay. So this is a 0.08. 0 years since 2017, the population is 8. Then, in 2020, it's been 3 years since 2017, so we're going to come up to 3 here. And it's going to be 26. That's about triple, a little more. So here's 26, and after 3 years, here's your population. That's what we're given. Now we expect that the population is going to be 84.5, ballpark, in another 3 years. So if we come up to 6 years, we should be up here around 84, 84.5, and that would give us a point up here. Question mark, is this going to be about right? Okay, well there we've interpreted our information on a graph, and we know, at least if we know to do what we've seen before and what I believe you probably did on the homework, because you got most of the problems correct. We're going to do an exponential model. Okay, so you can always use a b to the t in this case, and that's p equals a b to the t. This yields 2 equations. Okay, first of all, 8 equals ab to the 0. Of course, that's going to be really easy to solve for a, isn't it? And 26 equals ab to the 3rd. Again, yeah, coordinates of this point are 0, 8. So y is 0, or p is 0, because it's p now. P is 0. No, t is 0, okay, t is 0, when p is 8. Then, when t is 3, so t is 3 now, p is 26. That's given. Okay, that's simultaneous equations. Now, there are various ways to solve it, as we saw earlier. The way I usually solve these is I divide one equation by the other, because in that case A divides out. And we end up with the simple power of B equal to a simple number. We take a reciprocal power of both sides, and we get our value of B, plug back into either of the equations, we get our value of A. Okay, well, in this case it's particularly convenient because we have a b to the 0 here. We know what happens when t is 0, which means since b to the 0 is 1, that a has to be 8. Okay, so eight equals 8 times 1, so a is 8. Now the examples we did earlier, I didn't do the simplest possible case, but if you can set up a problem where t is 0, or whatever variable you have as the exponent is 0, makes it particularly easy to solve the system. Okay, so, and now that a is 8, the second equation becomes 26 equals 8b to the third. So b to the third power equals 26 over 8, and b equals 26 over 8 to the reciprocal power, the 1/3 power. Okay, 26 over 8 is 3.25, and 3.25 is pretty close to the square of 1.8, but that's not going to help us. 1.5 cubed is 3.37. So I'm going to say this is pretty close to I'm going to guess without thinking too deeply, so don't have a lot of confidence in that 8 there, but I'm going to say it's approximately 1.48. Come on. Okay. Thus, P equals AB to the T approximately equals 8 times 1.48 to the T power. There's our model. Now given that model, we can plug in 5, we can plug in 3. T equals 6, since population is, since time is measured from 2016. So P is 8 times 1.48 to the 6th. Okay, well, if 1.48 to the 3rd is 26 over 8, then 1.48 to the 6th will be the square of 26 over 8 to the 1/3. Okay, and I don't think I said the 1/3 before, but anyhow, this is the exact result. I can also write up here the exact equation, although in the case of a deer herd, exact is of, decent approximation is good enough, because you can't exactly predict how the herd is going to reproduce, okay? You can't predict how many are going to survive, what kind of winter you have, any disease that might come along and either limit the health of the herd or kill some of them. So there's so many factors that you're not going to get an exact population model for a deer herd. Now, if you're predicting financial calculations, those things have to be, now if you're trying to predict the stock market, you're in equally or even more uncertain territory. But if you're trying to predict payments on a loan or whatever, then you're going to do it precisely, and you're going to want to have completely precise results. If this is a principal on a loan or whatever, or a principal in an investment, you want these numbers to be exact. Okay, so the exact model that you would use if you were doing certain types of financial calculations would be P equals 8 times 26/8 to the 1/3. In this case then, the exact this is exact model. Again, the exact model is not that important for deer herd, but the exact model, if you needed an exact model for some other situation, would be 8 times 26/8 to the 1/3 raised to the 6th. Which would be 8 times 26/8 squared. And so I'm saying that's going to be approximately 84, and you can calculate that to verify the validity of this model. And then the population, 2025, T would be 8, since you're measuring time from 2017. So the population would be 8 approximately times 1.48, which is fine for the deer herd, even if I don't have a really great estimate there. Be that times 1.8 to the 8th. And I've said that might be approximately equal to maybe 170. Well, you've got your calculators. You ought to take a note on that and check it out. And if you want to just take a second and check it out, you can. You don't have to move the boards. It'll take you about 10 seconds to do that. And if you do, go ahead and tell me what you got. See how my 165 to 170 estimate works out. Okay, so I'm a little curious about that, but we're going to move on. Okay, we have this idea. I hope so. The idea simply is, if you know the values of an exponential function at two different values of the independent variable, the t in this case, then you can write out the form of the exponential function, and you can write two simultaneous equations, as we've done before, that you solve and get your predictions. If you can make some predictions based on good common sense or even bad common sense, as we did here, then that's even better for testing your model and making sure that it makes sense. Okay, so very good. We're going to move on now.